So back again with me, okay, อาจารย์ปัทมาพร here in Thailand at Kasetsart University, okay, at Bangkok, Thailand, of course. Okay, and today we are going to start with our RLC Source free circuits. And the first topic I'm going to do, though, is finding initial and final values. Okay, so maybe a review. Okay. We have done this with RC and RL circuit also, okay, the step-by-step approach. So I'm going to do it again, and there's something else also that you need to know. So the question is, I have a problem here, the circuit. There's a switch closed down at t equal to 0. This is 10 ohms, 1/20 farad, 2 ohms. There's a voltage drops here, across here. There is a 0.4 Henry. And of course there's a current here, right, I, going through an inductor. Okay, and the question is, find I at 0 plus V at 0 plus di at 0 plus di dt at 0 plus dv dt at 0 plus. Find I at infinities, the final values, and the voltage at infinities. So these are the 4 initial values and 2 final values that we have to find. So let's see. Well, the reason we can say that find it at 0 plus is also because I is the one that the current going through an inductor, so it's like IL, and V is a voltage drop across a capacitor. So therefore, of course, that means we can write our so-called rules for the capacitor inductor that the voltage across a capacitor cannot change instantaneously. So V0 plus is equal to V0 minus. And the current going through an inductor cannot change instantaneously. So I0 plus is equal to I0 minus. So therefore, we have to always find out what is there energy stored in our inductor or capacitor before the switch moved. Okay, it's actually become our priority to do that. Okay, so therefore we look at our circuit at t equal to 0 minus. Draw it out, please. You have to draw it out. Okay, don't imagine it in your head. Okay, so we're going to draw it out like this first. Let's just draw it. What does the switch look like? It was open, right, before t equal to 0. So therefore our 10 ohm is there. So it become like this, right? So 12 volt I V. Okay, well, the circuit has been like this for a long time, since t equal to minus infinities until up to t equal to 0 minus. Imagine it's a very long time, steady state reached, capacitors fully charged, inductor fully energized. So therefore, your capacitor would act like an open circuit. That's right. Those who remember, very good. Okay, your inductor then would act like, yes, short circuit, right? So therefore, there, your circuit would look like this, and this is 2 ohms. So therefore, my wonderful students, please use your knowledge that you have learned for the past 20 topics, okay, to solve this. So what is our I0 minus and V0 minus? So let's look at our current. Well, current come out from the source. The positive go through here, pass through 10 ohms. You have to know where your current's going, right? 10 ohms goes here, comes here, and go back. Oh, wonderful, wonderful. It's only one loop, right? Just like 10 and 2 in series and connected to the 12 volt. So therefore, I0 minus is simply using Ohm's law, 12 divided by 10 plus 2 is 12. So therefore, 1 amp. Okay, what about V? V at 0 minus. Well, you know your current I, right? 1 amp. So 1 amp going through here. Of course, V is a voltage drop across a capacitor. In this picture, it's also a voltage drop across the 2 ohms. So therefore, V equal to IR. So 1 amp times 2 is equal to 2 volt. But if you're more sophisticated and say, oh, okay, I see this right away, I can use voltage divider, right? So therefore, it's become 2 over 10 plus 2 times 12, so equal to 2 volt. So you get these values. So therefore, when t equal to 0 plus, when t equal to 0 plus, right, switch changes. Let's see. So what does your circuit look like? The switch closed down. Let's see. Let me look. So you come like this, right? And the switch closed down like this. This become like this. Inductor and your 12 volt, right? I, V. Okay. So therefore, since it's a voltage drop across a capacitor, so V0 plus also equal to V0 minus equal to 2 volt. The current, it happens to be, I happens to be the current going through an inductor, so I0 plus is equal to I at 0 minus equal to 1 amp. Okay, now the circuit, the switch closed down, so this becomes short, right? So this become like 10 ohm is being shorted out. So therefore, if I redraw my circuit, I can do it like this, right? So it becomes simply, this is like there's no resistor to be considered anymore, and we have the inductor like this. Okay, and this is 2 ohms. Oops, sorry, wrong. I want to get this. Maybe I'm a little picky here. Okay, so therefore this is 0.4 Henry. This is 1 over 20 farad, right? Yes. Okay. Now, next thing I want to find, okay, so I find this and this already. I want to find di dt and dv dt at 0. So I have to try to figure out, okay, where is the formula di dt? Where's the formula di dt? Where is it? Okay, which relationship has the equation of di dt? And di dt happens to be the current go through an inductor. So therefore, the relationship that you must be able to recall is VL equal to L di by dt. So let's look at how the current flows. Okay, so if I say that the current goes like this, right, I, so there's a voltage drop VL right here, okay, it goes here, right, the current goes here, then it's split into IC, right, and there's IR right here, okay, with the voltage drops. Now, if the relationship is that VL is equal to L di dt, if it's at t equal to 0 plus, that means VL at 0 plus equal to L di at 0 plus dt. So therefore, my di dt at t equal to 0, the one that I want, is simply VL at 0 plus divided by L. Or in another word, di dt at 0 plus is equal to VL at 0 plus divided by 0.4 Henry. The question is then, how to find VL at t equal to 0? Well, at t equal to 0 is this picture, right? Is this circuit. Well, V is right here. This is V of t, V at 0 plus, right? Here, this is V at 0 plus. So therefore, let's see. That means I can there's a sort of like a mesh, right, like this current. So if I write down KVL, right, KVL for this mesh right here, right, it would be minus 12 plus VL, right, at 0 plus V at 0 plus equal to 0. So therefore VL at 0 plus is equal to 12 minus V at 0 plus. Well, V at 0 plus is a voltage drop across a capacitor, which is right here, right? So 2. So therefore it's 12 minus 2 equal to 10 volt. So therefore I get my VL at t equal to 0 plus to be equal to 10. So therefore my dIdt at 0 plus is equal to VL at 0 plus divided by 0.4. So equal to 10 over 0.4 equal to 25 amp per second. So I got my dIdt there, right? Now dV dt at 0 plus, what is it? What is the formula that would have dV dt in it? Well, it's a relationship, right? IC equals C dVc by dt, right? So in this configurations, I'm going to redraw this because I don't want to scroll it up again. So 2 ohms, 1 over 20. This is IC, this is V. Volt I plus minus VL. Right, so let's see. So therefore, if I want to find dV, right, in this case it's V, not VC. So dV dt at 0 plus is equal to IC at 0 plus divided by C, right? And this is IC. Current I comes through here, go down IC, and then IR right here. So this is IC. How to find IC? Well, the current I comes through this junction, divided into two so-called 2 branches, right? So I write KCL, right? KCL at A, at node A. Okay, so at node A, I would have, well, I at 0 plus, right, equal to IC at 0 plus IR at 0 plus. Okay. Well, I at 0 plus we know, right, is equal to 1 amps. 1 amps equal to IC at 0 plus, we don't know. And IR at 0 plus is simply I equal to V over R. So therefore we know that V at 0 plus over R, which is 2. So therefore IC 0 plus would be equal to 1 minus V at 0 plus is, V 0 plus is what? 2, right? 2 over 2, right? So therefore this becomes 0 amp. So IC at 0 plus is 0 amps. So therefore our dV dt at 0 plus is equal to IC 0 plus divided by C. So it's 0 divided by 1 over 20 and up to be equal to 0 volt per second. So we got our 4th initial conditions. Okay. Now the 2 final values. The final values, of course, is at t equal to infinities. At t equal to infinities. Okay. So at t equal to infinities, right? This is your circuit. The circuit is going on like this for a long time, right? So your capacitor would act like an open circuit, right? Your inductor acts like a short circuit. So 12 volt, 2 ohms, V and I. So this is your circuit to analyze at t equal to infinities. So therefore, I at infinities would be equal to simply 12 volt divided by 2 ohms equal to 6 amps. And V at infinities would be equal to simply 12 volt. So this is the way to find initials. This is an example, okay, to find initial values and final values. So now we can start with our source-free RLC circuit. Okay. Right, so ready. Okay, it's one of the long and quite difficult topics, okay, topic for this course. Okay, so I'm going to start with source-free parallel RLC circuit. Okay, so this is the R L C, no source. There's a voltage right here at the node, right? There's a current IR, current IL, and current through a capacitor IC. And we will assume that, okay, given that, okay, there is an energy stored, okay, in the capacitor and inductor. Okay, so there would be, IL at 0 equals to some values I0, and V, right, V across the capacitor, which is in this case is also V, okay, has some value, initial values. Okay, we want to find V of t for t greater than 0, okay, or at this point when we have RLC source-free circuit. Okay, so having things in parallel, different current going through each branches. So we're going to start off with our KCL at node V of t. So it is IR plus IL plus IC equal to 0. So therefore, we want to find V, right? So IR is V over R plus IL is 1 over L, integrate V dt. I'm going to go real fast and simple, okay? And sort of like ignore all the proper way of writing in math terms. So plus C dV by dt equal to 0, okay? And I'm going to take the derivative again to get rid of the integration sign, the integral sign, and divide everything by the capacitor. And the formula I will receive is d square V dt square plus 1 over RC dV dt plus 1 over LC V equal to 0. Okay, so back to second order differential equations. Okay, now I'm going to jump into our characteristic equations. Okay, I'm going to give you a sort of like a shortcut that we're going to say that, well, I'm going to represent d square V dt square with s square, and replace that dV dt with simply that term s. So therefore our characteristic equation would turn out to be s square plus 1 over RCS plus 1 over LC equal to 0. So this is the characteristic equations, and you have to find the roots S1 and S2. Okay, so and if you apply that quadratic formula things, right, it would give you that S1 and S2 will be in the form of minus 1 over 2RC, okay, plus minus square root of 1 over 2RC square minus 1 over LC. And if we define, let a symbol alpha, okay, alpha equal to 1 over 2RC, and omega naught equal to 1 over square root of LC, okay, where alpha, the unit is Nepper, Nepper per second. Okay, and omega naught is called the unit is radian per second, and it's called the resonant frequency. Okay, right, and so therefore we can write S1 and S2 as minus alpha plus minus square root of alpha square minus omega naught square. Okay, so this would be your roots. Okay, right? Okay, and of course your S1 and S2 can be put into overdamped case, critically damped case, or underdamped case. Okay, so that's how you get your response. And of course, since this has no force functions, it's a source free, so therefore your solution would consist of only the natural response. All right, so now next, so this is the series so-called the parallel RLC source free circuit, right? So depending on this S1 and S2, right, you can have your answer in an overdamped case or critically damped or underdamped. Okay, so therefore now I'm going to go next into source free series RLC, source free series RLC circuit. So it was parallel. So now so if there's a current flowing like this, current I, right? So current go through R, so there's VR, VL, and V across C, like this. Okay, so it's a mesh, right? So we write KVL of this mesh. So VR plus VL plus VC equal to 0, right? We want to find the current I, express this in the current I. So therefore VR is R times I, right? VL is L di by dt, because I go through all three elements, plus 1 over C integrate I equal to 0 from minus infinity to t, whatever. So therefore differentiate everything and you get R di dt plus L d square I dt square plus 1 over C I equal to 0, right? No source, so equal to 0. Or in other words, you would have d square I dt square plus L over R, plus R over L plus R over L di dt plus 1 over LC I equal to 0. So again, second order differential equations, right? So homogeneous because it's equated to be equal to 0. Okay, so if well, in this case, let's see. If I say that, well, if I let my solution, right, I of t to become equal to a e to the st, okay, and then substitute it back into the second order equations, I would have a s square e to the st plus a r over l s e to the st plus a over lc e to the st equal to 0. So factor a to the st out, so I would have a e to the st times s square plus r over ls plus 1 over lc equal to 0. So therefore, my characteristic equation is then s square plus r over ls plus 1 over lc equal to 0. Okay. And using the formula from your algebra class, right, your S1, if I'm going to divide it like this, I separate it out. S1 is minus r over 2l plus square root of r over 2l square minus 1 over lc. And my S2 would be equal to minus r over 2l minus square root of r over 2l square minus 1 over lc. Okay, and again, if I said I let alpha equal to r over 2l, right, and omega naught, my resonant frequency, equal to 1 over square root of lc. Okay, right, my alpha is my damping ratio. Okay, then I can write my S1 as minus alpha plus square root of alpha square minus omega naught square. My S2 equal to minus alpha minus square root of alpha square minus omega naught square. So these are my roots. Okay, S1 and S2. And of course, right, depending on the value of alpha and omega, right, these two can be, again, right, it could be overdamp, right, critically damp, or underdamp. So this is the series RLC circuit. So if I'm going to give an example, okay, let's see. If I have parallel, so I'm going to have example for parallel RLC source free circuit. Okay, example. I'm going to put values inside. So these questions, well, if I have R, right, L, and C source free. Okay, this is V of t, L, C. Given V at 0 is equal to 5 volt, IL at 0, right? So that's IL, IR, and IC like this, equal to 0 amp, okay, as the initial values for these two. L is equal to 1 Henry, C is equal to 10 millifarad, okay, and R equal to 1.923 ohms, right? And I want to find V of t. Find V of t at t greater than 0. Okay. So therefore, I start with alpha then equal to, right? It's simply this term right here, all this form that we did, okay, and all the alphas and omega naught and the roots. So therefore, alpha is equal to 1 over 2 RC, so equal to 1 over 2 times R is 1.923 times C is 10 millifarad, and the answer is 26. Okay, and omega naught, okay, omega naught is 1 over square root of LC. So therefore, it's equal to 1 over square root of L is 1 Henry times C is 10 times 10 to the minus 3. So the answer is 10 radian per sec, and this is Nepper per sec. Okay, so therefore, my S1 and 2, my S1 and S2 are minus 26, right, plus minus square root of 26 square minus 10 square. So the answer is minus 2, and minus 50. So this is the first case, right? S1 and S2 are distinct. So therefore, my V of t is equal to A1 e to the minus 2t plus A2 e to the minus 50t volt. So this is the solution I've got, right? So therefore, this is an overdamped case. Okay, now the problem is not done yet because you have to find the coefficient A1 and A2. Okay, so to solve for A1 and A2, you need initial condition. So there are two of them that you need is then V at 0 and dV dt at 0. Okay, so the first thing we know already that the problem has given you that, it was given that V at 0 is equal to 5 volt. But we still need to find dV dt at 0. Okay. So let's look at what is dV dt at 0. Okay, let's look at the circuit again. So the circuit was what we did, R, right, L, C. So R, L, C. IR, IL, IC, and this is your V of t with respect to ground. Okay. So we're going to write down KCL at V. So we would have IR plus IL plus IC equal to 0, right? So if we say at t equal to 0, so IR at 0 plus IL at 0 plus IC at 0 equal to 0. But we want dV dt, correct? The only place that formula has dV dt in is your IC. The current going through a capacitor is equal to dVc dt, dV dt. So therefore, this become C dV dt at 0, right, equal to 0. IR, right, V equal to IR, I equal to V over R. So therefore, this is V at 0 over R. And R in this case was 1.923, right? Plus IL at 0. IL at 0 was given to be 0, right? The problem say that, where's the problem? Here, IL at 0 is equal to 0 amps. So this is 0 amp. So therefore, we would get dV dt, and V at 0, this is 5 volt, right? 5 volt. dV dt at 0 is equal to minus 5, right? Minus 5 over 1.923 times C, 10 times 10 to the minus 3. Okay. So the answer is minus 260 volt per sec. Okay. So therefore, now we can substitute this to find A1 and A2. Right? So from our solution was V of t equal to A1 e to the minus 2t plus A2 e to the minus 50t volt. Our first initial conditions, right, V at 0 is equal to 5. Substitute it in t equal to 0, you get A1, right, e to the 0 plus A2 e to the 0. So therefore equal to, so therefore you will get A1 plus A2 equal to 5. Right, this is your first equations. Okay. The second one is dV dt at 0 is equal to minus 260. Then you have to differentiate V of t, correct? So it become minus 2 A1, right? Substitute 0 right there, e to the 0, minus 50 A2 e to the 0. So you would get minus 2A1 minus 50A2 equal to minus 260. So this is your second equations. So using solve for N2, right? using both of that, you can use Cramer's rules or whatever, right? You get A1 to become, so A1 is equal to minus 0.208, A2 is equal to 5.208. So therefore, your final answers, V of t equal to minus 0.208 e to the minus 2t plus 5.208 e to the minus 50t volt for t greater than 0 for this problem. So you get it? Right? So I'm going to do the next one, next example. Right. So in this case, same problem. Okay, same problem, but in this time R equal to 5 ohms. All the values are the same, keep them the same. Change only R, the resistor values. Okay, so repeat all those procedure that we just did, right? So alpha would be equal to 1 over 2 RC equal to 1 over 2 times 5 times 10 times 10 to the minus 3, which is your C, equal to 10. Okay, your omega naught, oh, your alpha, right? Well, when you do this, right, your omega, one omega would be the same, right? Because 1 over 2 RC, your omega here, right, is also equal to 10. Your omega is also equal to 10. Your omega is also equal to 10. So therefore, your S1 and S2, right, turns out to be equal to minus 10. So they are repeated root. They're repeated roots. So therefore, your answer, your general answer first would be equal to A1 plus A2t e to the minus 10t volt. This is your answer. Now we have to find A1 and A2. Find A1 and A2. Okay. We have to find again what dV, well, the initial value, the first one, V0 is equal to 5 volt, right? But we have to find dV dt at 0. What is it? Okay. So the procedure is the same because it's the same problem. Okay. So therefore, in this case, your dV dt at 0 would be equal to minus 5 over 5 times 10 times 10 to the minus 3, and the answer is minus 100. So therefore, using that initial values, so V at 0 is equal to 5, so equal to A1, right, plus A2 times 0, e to the minus 0, right? So therefore, it's equal to A1. So therefore, your A1 is equal to 5. Okay. Now, dV dt at 0 equal to minus 50. Oops, did I say minus 100? Oh, minus 100. Minus 100, sorry. Minus 100. You have to differentiate your V of t, right? So it would be equal to minus 10 A1, right? Minus 10 A2 times t, so 0, okay, plus A2 e to the minus 10 times 0, so 0. Right? So therefore, you will end up with minus 100 equal to minus 10 A1 plus A2, right? So this is your first equation, this is second equations. So using 1 and 2, okay, you get A1 equal to 5, A2 equal to minus 50. So the answer is V of t equal to 5 minus 50t e to the minus 10t volt. So this is another case, right? So why don't you go and do it yourself? Case number 3, you can guess what the answer would turn out to, what type of case would be. So same problems, but change R to 6.25 ohms. Okay, change R to 6.25 ohm, and you can do it by yourself. Okay, and I'll give you the answer. At the end, you should get 5 cosine 6t minus 6.667 sine 6t times e to the minus 8t volt. So please go and do it yourself, practice. Okay, you maybe have to review how to differentiate cos and sine term. Okay, so all right, so this is it for today. Thank you very much. See you next class.